is function of x. X is the distance from the leading edge of a flat plate, and then Reynolds number, and then Prandtl number. So if we talk about the average Nusselt number, so in that case, the x dependence is lost, and we only get the dependence of Reynolds number and Prandtl number on Nusselt number. So now in chapter we are going to use this functional form of Nusselt number to discuss many empirical correlations in case of turbulent flow for two types of flow. The first type of flow is the external flow, and in that we would be discussing external force convection. So first of all, we would discuss the fundamentals of external force convection. In that, we would also discuss the fundamentals of external flows like drag and lift, which I gave the introduction at the last of the last lecture. And then we would discuss flow over flat plate, that how can we determine the Nusselt number for flow over flat plate, and flow over cylinder spheres, and then one big practical application of external flow is flow over tube banks. So in that we have got multiple tubes arranged in one after other, and then we kind of get the heat transfer from that tube bank. So these are the four topics which we would be covering in this chapter. So this is chapter number 7 of your textbook Angels. So now uh, let me quickly recap which we discussed yesterday about the external flows. So first of all, the practical application of external flows, as we discussed, that the flow over any automotive or any ship or aeroplane, missiles. So that is example of external flows, as well as flow over buildings, and then flow over transformers and things like that. So all those flows come in external flow. And then what is a drag force? Drag force is the force a fluid exerts on a body in the flow direction. So that is in the flow direction, that is the important thing. So that is the force which is exerted by the fluid on a body, and then equal and opposite force is exerted on a fluid, on that fluid by that body by the virtue of Newton's third law of motion. So drag is due to combined, as we discussed in yesterday's lecture, that drag force is combined effect of pressure forces, which is called pressure drag, and then wall shear forces, which is friction drag or skin friction drag, as I discussed in yesterday's lecture. And the important thing is that drag force is parallel to the flow direction. So that is the drag force. And then the second force, which is encountered in fluid flow situation, that is lift. So lift is generated due to combined effect of pressure and shear forces in the perpendicular direction to the flow. So that is the main cause of lift force when we have got forces in the perpendicular direction. And then we discussed about that what is pressure drag. So for that we took a bluff body in which the flow is coming here, and then we know that there would be a stagnation point, and then the streamlines would kind of diverge like this to accommodate the presence of this body. So then after downstream of this vertical wall, we can take it vertical wall, we would have some area where there is a flow separation or the velocity which is different from the free stream velocity. So that area is called wake region. Wake, W-A-K-E. So that is the wake region. So because we know that the stagnation pressure is on the front of this body, and then on the backward region, because we have got flow separation. So in the wake region, the pressure is always low, and on the frontal side the pressure is always high. So there is pressure difference in front and on the on the downstream area. So that pressure difference gives rise to pressure drag. So drag coefficient in terms, if we want to write it, that is C, we represent it with CD, and that is coefficient of drag, and that is equal to FD divided by half rho U square, U infinity square into area. So hopefully you would be coming across this formula in your FM2 course as well, in the chapter of external flow very soon. And then this was pressure drag we were talking about, and then uh, uh, component of drag directly produced due to the wall shear stress. That is the second component, that is skin friction drag or friction drag. And then a component of drag which I have explained earlier, that is directly produced due to the pressure difference. Here it should be pressure difference, is called the pressure drag, or we call it also the form drag. It means that it depends upon the geometry of that orientation of that body, that if it is perpendicular to that flow, the frontal area is more, then there would be pressure drag. If the frontal area mean the where the flow is perpendicular, if that area is more, then the pressure drag would be more. So form drag or pressure drag depends on the shape of the object, that whether that is a bluff body. If it is a streamlined body, then the pressure drag would be minimal. So skin friction drag in that case, if the body is a is a very thin body or streamlined body, so in that case the skin friction drag would be more, because the in that case the frontal area is minimal and the surface area on which the flow is happening, that is maximum. So that's why frictional force or shear force would be more in that case. So the total drag on a body, if we want to determine that, that is the sum of the friction drag and the pressure drag. And similarly, we can write that the coefficient of drag is the sum of friction, skin friction coefficient plus pressure drag coefficient. So these are the two components in coefficient of drag. So for flow over a flat plate, so which means if we take this body and we rotate it 90 degrees, then it would be a flow over a flat plate. In that case, the frontal area would be only this thing, this thickness, which is minimal, and the surface area would be this frontal area. So in that case, skin friction would be more. So that's why we can neglect the contribution of pressure drag in that case, because the frontal area would be minimum. So the CD friction is almost equal to CF. So friction drag is, because for the friction drag we use the formula mu into du upon dy. So that's why it is a strong function of viscosity. And then it is also a strong function of surface roughness. If the surface roughness is more, then the friction drag would be more. If the surface roughness is so it means that if the surface is polished, in that case the friction drag would be less. So you would be coming across Moody chart in I think chapter number 8 of your book in FM2, in which you would study the effect of surface roughness in case of flow inside a pipe. Right. So now we turn our attention to the calculation of drag and heat transfer calculation in external flow. So in the chapter number 6, as we discussed, the functional form of the Nusselt number, that is, as I started my today's lecture from that recap, that if we are determining the local Nusselt number, which is depending upon the x location, for for that flow, it depends upon x star, Reynolds number, and Prandtl number. And if we are talking about average Nusselt number, that is only a function of Reynolds number and Prandtl number. So now it is just a matter that how we represent this functional form into an empirical correlation. So we can have many types of correlation from here. It can involve only the product of this two exponent to something, and then it can be some exponential function and things like that. So the most simplest form of empirical form of this functional of this function, that would be a power law. So power law can be represented like this, that Nusselt number is equal to C, which is a constant, then Reynolds number raised to power m into Prandtl number raised to power n. So now the value of C, m, and n, they would be these values would be determined for a particular flow by the conduct of experiments. That once we conduct the experiment and then we use some curve fitting techniques to determine the value of this constant C, m, and n. So you know that software like MATLAB, we can easily do the curve fitting if we have that data in XY plot. So that is quite simple thing to do. So we can always determine the values of C, M, and N. So that is the simplest form of that functional form in terms of empirical correlation. And I would repeat again, this value of C, M, and N, that would come from the curve fitting of of the data which is produced by the experiments which we conduct. So now, in order to determine this Reynolds number and Prandtl number, because if you know the definition of Reynolds number, that is rho Vd upon mu, and rho Vl upon mu in case of external flow. Prandtl number is mu upon alpha. So because these mu, rho, and alpha, these are dependent, they are strong function of temperature. No, because in case of convection, we have got two temperatures. One is the free stream temperature, and one is the surface temperature. And they are quite different, because either we are cooling the solid surface or we are heating the solid surface. So in both cases, the temperature Ts and T infinity, they are quite different values. So because these fluid properties mu, rho, and alpha, they are kind of strong dependent upon temperature. So it means that we need to use some mean temperature value. So for that we use film temperature. So that is the average of Ts plus T infinity divided by 2. So let's suppose we are trying to cool a surface which is at 80 degrees. So the air which is coming onto that solid surface, that is at 10 degrees. So Tf, which is the film temperature, that would be equal to 10 plus 80 divided by 2. So that would be equal to 45 degrees centigrade. So once we get the film temperature, we can calculate mu, rho, and alpha from the tables. And then we can calculate Reynolds number and Prandtl number for by using those values. So I hope that the concept of film temperature is clear to you. So now
ये
how to
पास करिए इनका बता दें दोबारा फिल्म
uh,
टेम्परेचर का
जी Atif, is it Atif? Is this
शायद
Atif? Okay, Shariz. Okay, thank you. So Shariz is asking again that why do we need film temperature? The thing is, if you look at this formula, this power law, because the Nusselt number is dependent upon Reynolds number and Prandtl number. Now, Reynolds number in the how do we define Reynolds number for a flow? We need to know rho, we need to know u infinity into length of the flat plate divided by mu. So we need to know these two physical properties, which are rho and mu. And then for the calculation of Prandtl number, we need to know nu. Nu is the kinematic viscosity divided by alpha, which is thermal diffusivity. So in order to get these properties, because they are strong function of temperature, It means that if we evaluate these properties at 10 degree, it would be different value, and if we evaluate at 100 degree, it would be quite different value. So it means Reynolds number and Prandtl number, they are strong function of temperature. Now, in case of convection, we have got two extreme temperatures. One is the temperature of the that body, which is represented by Ts, and the other temperature is T infinity. So they are quite different usually. Whether we are cooling the solid surface or we are heating the solid surface. So it means that the problem is that at which temperature we should get these values of mu, rho, and infinity. So for that, what we do that, because we cannot use either T infinity or Ts, so the best possible thing to do is that we can take the average of these two extreme temperature limits, which are Ts and T infinity, and then we determine these properties at that mean temperature. So that mean temperature is called film temperature, right? So, Shadid, is it clear?
Clear, sir. Thank you.
Okay, ji. So once we get this Reynolds number, Prandtl number, then we can calculate this local Nusselt number at different x locations on that flat plate. So if we do that, we can have a local Nusselt number or h, and then if we want to calculate the average Nusselt number, we can always do the integration for the drag coefficient, and then for the calculation of Nusselt number, because Nusselt number is HL upon K, so I have written it in terms of H, not Nusselt number. So, but the functional form would always be, all the correlations would be given in terms of Nusselt number, not in terms of H, because Nusselt number is the non-dimensional temperature gradient at y is equal to 0, as we discussed in the last class. So because we are more, why we calculate this average value, because we are more interested in one numerical value which we can use in our calculation for the Newton law of cooling. Because if we determine the local Nusselt number or local H value, then we need to do the integration of that Newton law of cooling, which we don't want. So we just want to apply Q is equal to HAS Ts minus T infinity, which is quite simple in doing the calculation. So that's why we want to calculate an average value of H, and that is the same value which we used in conduction analysis. Whenever we had got some convection phenomena, we were given a numerical value of H, like 20 watt per meter square Kelvin or 100 watt per meter square Kelvin, like in that transient analysis, then 2D steady state, and then 1D steady state, we always been given a numerical value of H. So here, for numerical value calculation of H, we need to know the, first of all, the empirical correlation of Nusselt number in terms of Reynolds number and Prandtl number. From there, we would get Nusselt number, and then from Nusselt number, we would calculate H. Right. So that is our line of action, or line of doing the analysis in terms of convection, because we discussed the calculation of H is the major challenge for the convection problems. So this was just the introduction, that how we are going to extend our discussion for the external force convection. So first of all, we would discuss flow over a flat plate. So that is the first external flow scenario which we are going to discuss. So for the flow over a flat plate, the critical Reynolds number is equal to, as I also told you in the last class, that is around 5 lakhs or half million. And the definition of Reynolds number is rho into U infinity into X critical divided by mu. So X critical is the distance from the leading edge of the flat plate where the flow becomes into contact with the that flat plate, and then that is the length up till where the flow becomes laminar, and after that the flow transition begins. And if you see here is this line, it is showing you the thickness of the boundary layer. As I explained in the last class, that it grows along the flow direction, and Ts is the temperature here. This vertical line up till here, the flow is laminar. After that, the flow transition would occur because the Reynolds number would be greater than 5 million, 5 lakh. Why here the Reynolds number is increasing with length? Because Reynolds number definition, there is x. So it means that if we go along the flow direction, x would increase, and in turn Reynolds number would increase, right? So there would be some x value at which the Reynolds number would become equal to 5 lakh, and after that the flow transition would start, and then the boundary layer would become turbulent. So now, how to calculate this delta value, which is boundary layer thickness, as I explained in the last class, that either we can do the analytic solution of Blasius, which was only valid for laminar flow. So for the laminar flow, Blasius did this analysis and told us that if we want to know the value of velocity boundary layer thickness, that would be equal to 5x divided by Reynolds number, and Cf, which is the friction coefficient, that would be equal to this. So that is only can be done analytically by using the Blasius solution, which is similarity solution only for the laminar flow, because in that we can do the simplification of the Navier-Stokes equation quite easily. But for the turbulent flow, there is no simplification that can be done, because in that there are turbulent fluctuations. So in that case, we cannot simplify the equation to the ordinary differential equation. So it means that Blasius solution cannot be applicable. So for the turbulent flow, if you see this relation of 0.3382x divided by Reynolds number raised to power zero point 0.2, so that is kind of empirical correlation which has been gotten from experiment. And similarly for the CF, this is also an empirical correlation which has been obtained by doing the experiment. So if we want to know here that, okay, this is CFX, it is a local friction coefficient which is dependent upon x location. So if we want to know the average CFX value, what we do, that we integrate it from 0 to capital L. Capital L is the total length of the flat plate, and then uh, outside the integration we would have 1 upon L. So if we do that simple integration, we can calculate the CF value, which is the friction coefficient for the laminar flow. If you see, if 0.664 into 2 would be equal to 1.328. So we can easily do this integration, and then the average friction coefficient would be given, can be obtained for the laminar flow and for the turbulent flow. Okay, so this is what we have talked here on this slide, that is only related with the fluid flow, right? And that you would also study in your FM2 course, hopefully. But our main interest for this is the Nusselt number correlation, right? Because we are more interested in case of convection, we want to know H value. So on this slide, there is no mention of any heat transfer Nusselt number or H value calculation. So, because in the book, these two things, this friction coefficient, they have combined in force convection. They are also discussing the friction coefficient. So I just thought that it would be good idea to show you these relations, but these are only for the fluid flow situation. So for the convection case particularly, we need to know Nusselt number. So for the Nusselt number, the now as we discussed power law, if you know here on this slide, if you can see that we discussed about the power law for the empirical correlation, where C was a constant, M is also, M and N, they are also a constant which would be determined by the experiments. So here, that power law formation you can easily see. Here the value of C is 0.332, then Reynolds number, now M value is equal to zero point 0.5, then N value is 1 by 3, which is 0.334. So you can see that for the laminar flow, local Nusselt number would be equal to this value, and it is only applicable when Prandtl number is greater than 0.60. This formula is only applicable when Prandtl number is greater than 0.60. And then for the turbulent flow, you can easily see that the value of C is different, 0.0296 instead of 0.332, and then Reynolds number is zero point 0.8, that power. Here it was 0.5, and then Prandtl number. So it means that the Nusselt number is largely independent of whether that is that Prandtl number is the same function for the laminar and turbulent flow. So Prandtl number doesn't change much in case of laminar and turbulent flow. So this was local Nusselt number. So if we want to know the average Nusselt number, we need to integrate these two equations. So if we do the integration, you can easily see 0.332. It becomes after integration 0.664, and then Reynolds number. Now here it is Reynolds REX. It is REL, which is the representing the Reynolds number at the right edge of the flat plate, which is, it means instead of x here, it would be the length of that flat plate, right? So once we get Nusselt number from these relations, then we can calculate h value by multiplying it with k and dividing it by h, because dividing it by L, capital L, because we want to calculate h, which is convection coefficient, and we need to use it in newtons of cooling for the determination of heat transfer by convection. So similarly for the Nusselt number, we can do this. So laminar flow, we can use this formula. For the turbulent flow, we can use this formula. But the problem is that if I take you back a little bit on this, if you look at this figure, you can easily see that whenever the flow starts, some portion of it is laminar and some portion of it is turbulent. So if the flat plate length is so long that we say that 90% of the flow was turbulent, then we can easily use only the correlation for the turbulent flow. But what if the flat plate length is such that half of the length the flow was laminar, then the half of the flow was turbulent, or rather, like, laminar flow is more than 10% or 20% of that whole length, then we need to use some combined formula for that. Then we cannot use the only the formula for the laminar or entirely the formula for the turbulent. Then we need to correct our original. We need to have the combined effect of laminar and turbulent flow. So in that case, if the flat plate is not very long, how do we define that long? It is not mentioned in the book, but for me, if the length of the flat plate is such that the 90% of the flow is turbulent, then we can use only the formula which is applicable for the turbulent flow, right? But if it is that turbulent flow region is less than 90%, then we need to cater for the initial laminar region. So in that case, that correction, if you see, then for the CF, if you know 0.0074 upon this Reynolds number, if you see this formula, it is written here. It is only for the turbulent flow, right? The last formula is 0.074 Reynolds number 1 raised to power zero point 0.2. So now if you see here, we are subtracting something from that. So we are decreasing the friction coefficient. So this thing which is being subtracted, That is the contribution of that laminar region, because in the laminar region the drag force would be less. So it means that we are considering that laminar region and decreasing the overall friction coefficient, because this first term, it is only for the turbulent flow. So if we consider the laminar portion as well, so the combined value of skin friction should be less than the value which is calculated from the only turbulent assumption. So that was the first term, right? So I hope that this point is clear. So on the same lines, we can do the correction for the Nusselt number, that here that 871 it is being subtracted. So if you know 0.037 Reynolds number, point 0.8, that was mentioned here in the last formula for the turbulent flow. 0.037 Reynolds number, point 0.8, and into Prandtl number 1 by 3. Now here we have subtracted minus 871 to have to consider. If you know, if you see this this curve here, you can easily see that the H value or the Nusselt number value for the laminar flow, it is less as compared to the turbulent flow, because in turbulent flow there is rapid mixing of heat due to the chaotic motion. So in that case, Nusselt number or H value is quite high. And as the boundary layer grows, the H value and Nusselt number values decreases, because partial T by partial Y at Y is equal to 0 decreases. So along the boundary layer, so that so consequently H value also decreases as the boundary layer grows in laminar to turbulent. So, but when the laminar to turbulent transition happens, you can see that sudden jump, this vertical line, that is showing that H value has increased suddenly from laminar to turbulent. So that is the example of that when you kind of rotate your a spoon in a cup of tea to mix that sugar. So that is you are trying to make it turbulent. So to enhance the mixing of that sugar particles. So that heat transfer is that analogy of that mass transfer. So in that case, we can say that for the turbulent case, the heat transfer increases rapidly. So that is shown by the increase in H value as the flow moves from laminar to turbulent region, right? So I hope, and then all these relations for the turbulent flows, they are from the empirical correlations. They are not derived from some fundamental principles, but rather they are formulated by the experiments conducted. And then after the conduct of experiments, we do the curve fitting, and then we get these relations like this. So I hope that this point is clear to all of you. And then if we have got a certain situation that in the beginning there was no heat transfer, but that was at the room temperature, then we have got some portion where there was some heat transfer as well happening. So it means that in that case the velocity boundary layer would start from this tip, but the thermal boundary layer would start after a delay of this parameter zeta. If you see that initial unheated length, which is represented by zeta parameter here. So for that, there would be very formidable relations, which you can see that they are quite complex. So in that case, Nusselt number can be calculated from the same relation for the, but there is something in the denominator to accommodate for that unheated initial length. So that zeta parameter is the length which is unheated in the beginning of the flat plane. So there is something that, so local Nusselt number, and then we can have average coefficient by numerical integration, because we cannot do simple integration for this. So we need to know about some numerical integration techniques, which you must have learned something in your, but you don't need to worry about that, how this relation came from here to here. So all you need to know that why we have got this parameter in the denominator, it is just to accommodate this unheated length. So in that case, Nusselt number would be a little bit different from the standard case. So, and then if up to now we have discussed only the cases where the surface temperature is known to us. But what if on that flat plate we are given the flux value rather than the surface temperature? So in that case, when the flux flat plate is subjected to uniform heat flux, then it is just like giving the uniform heat flux to a pan which is on an gas oven. So that is the case where we provide uniform heat flux. So in that case, if we want to know Nusselt number, then for that we need to use these relations. So now the C value is different for the laminar and turbulent flows, and then we can use these empirical correlations if the problem involves some uniform heat flux rather than the uniform temperature at that boundary. So if the boundary condition is different, we can always use different kind of correlation. So is there any query in this problem, which in this discussion about the Nusselt number correlations? So we have discussed the correlation for the flat plate, flow over a flat plate for laminar and turbulent flows. Then we discussed the combined effect of laminar turbulent flows for the Nusselt number, and then in the last we discussed the flat plate with unheated uh, initial length, started length. It should be initial length, and then uh, if we have got the boundary condition of uniform heat flux. So I hope that it is clear that why we use Russell number. Now we quickly do one numerical problem. So now engine oil at 60 degree flows over the upper surface of a 5 meter long flat plate whose temperature is 20 degree. Now TS is 20 degree, engine oil is 60 degrees. So now we are heating this flat surface, flat plate, and determine the total drag force. We need to know the drag force. So in that case, if we need to know the drag force, we need to know CF value, because then once CF is known, then we can calculate drag force, that is equal to CF is equal to F divided by half rho u square into area. And so, and the rate of heat transfer per unit width of the entire plate. So a surface area would be length into 1, so 5 into 1 meter square. So first of all, we need to determine film temperature. So film temperature would be equal to 60 plus 20 divided by 2, which is 40 degree. So at 40 degree from the table, we can determine the value of rho for the oil, which is 876, Prandtl number, K value for the oil, and then kinematic viscosity of the oil at 40 degree, which we can always get from the tables for the engine oil. So these properties are known. Once these properties are known, then first of all, we need to determine that whether the flow over this is entirely laminar or not. So in order to do it, we can calculate the Reynolds number at the right edge, which is the at the length 5 meters. So if we calculate that, that would be equal to v velocity is 2 meters, u infinity basically. I have used v because in the statement it is showing you v, which is the symbol they have used. So but it is u infinity. Any comment? Any query?
No, sir.
Okay, thank you. So V into length of the plate, which is 5 meters. 2 into 5, 2 meter per second is the free stream velocity. 5 is the length of the flat plate. Because why are we determining it here? Because we want to know that at this point, if Reynolds number is more than 5 into 10 to the power 5, then it would be combined laminar plus turbulent. But if it is less than that, then it would be laminar flow. So if we calculate kinematic viscosity is given at 242 into 10 to the power minus 6. So if we calculate that value, it comes out to be 41,300. So it is less than 5 lakh. So because it is less than 5 lakh, so it means that over the entire flow over this flat plate is less than less than is less than is totally laminar. So it means that now we can use the correlation which we determined for the laminar flow. So for the laminar flow, if you know the if you want to know the average friction coefficient, that is equal to 1.328. Yes, anything you want to add, Sharif?
सर ये रेनॉल्ड नंबर का फॉर्मूला कौन सा यूज किया?
जी is this Heather Ali?
जी सर.
जी रेनॉल्ड्स नंबर का फार्मूला होता है ना रो यू इंफिनिटी इंटू लेंथ डिवाइडेड बाय म्यू, यही फार्मूला होता है हैदर.
जी सर.
तो अगर म्यू को रो से डिवाइड किया जाए, म्यू तो होती है ना एब्सोल्यूट विस्कोसिटी, अगर उसको म्यू को रो से डिवाइड किया जाए तो वो बन जाती है काइनेमेटिक विस्कोसिटी. ठीक है, जिसको हम न्यू से रिप्रेजेंट करते हैं. ठीक है, तो हमने वही किया ना, रो को डिनोमिनेटर में ले गए हैं तो म्यू अपॉन रो को मैंने न्यू बना दिया है, और ये जो है यू इंफिनिटी जो यहाँ पे वी है 2 मीटर पर सेकेंड लेंथ, दैट इज. बेटा आपकी आवाज कट रही है, प्लीज कैन यू रिपीट योर क्यूरी. जी हैदर, इज इट क्लियर?
यस सर.
ओके जी. हैदर ने तो उसके अलावा भी समवन एल्स वाज ट्राइंग टू आस्क समथिंग. प्लीज आस्क अगेन, आई कुडंट हियर यू फर्स्ट टाइम. प्लीज ट्राई इट अगेन इफ यू हैव गॉट एनी क्वेरी. Okay ji, so it seems that that query has been resolved somehow, so that is good. So 2 into 5, so I hope that now we know that how we have calculated Reynolds number. Now as I mentioned that here we can use this formula for the laminar flow. The second last formula on this slide, CF is equal to 1.328 divided by Reynolds number at the right edge into 1 by 2. So if we do that, 1.328 Reynolds number, it was 1 by 2, so we can write it minus 0.5, so that would be equal to 0.0207. And now we can calculate drag force. Drag force would be equal to, because CF is equal to FD divided by half rho U squared into area. So for the calculation of FD, we multiply the denominator which was here with the CF, which is half rho U square into surface area. So CF we have already calculated. Rho AS, that is 5 into 1. 1 is the unit width, and then rho value is 876. U infinity, that is 2 square. So it means that the fluid would have a drag force of 181 Newton on the surface, and the equal and opposite force would be exerted by the fluid by that solid body in the negative x direction on the fluid. So that is the 181 Newton. And now the second thing, we need to determine the heat transfer rate. For the determination of heat transfer rate, Q is equal to HAS into TS minus T infinity. So the only unknown here is H. AS is known, TS is known, and T infinity is known. So for the calculation of H, we need to know Nusselt number. So for the Nusselt number, if you see that for the average Nusselt number, we can use this formula, right? For the laminar flow average Nusselt number, we can use 0.664 Reynolds number, zero point 0.5 raised to power zero point 0.5 Prandtl number raised to power 1 by 3. So we can use this formula. So if we use this formula here, so Nusselt number would be equal to 0.664, and then if we determine that Nusselt number, that comes out to be 1918. Now you can easily see that the convection is very dominant in this case, because Nusselt number, when it is equal to 1, that is the case of pure conduction in the fluid. Now the convection phenomena is very dominant. It is like 2000 times more than uh, which we would have when it has got stationary fluid. So the convection coefficient from this formula, if we know the Nusselt number 1918, we can multiply it with K divided by the length of the flat plate to calculate this H value, and then we can calculate Q, which is H into AS into T infinity minus TS. So if you understand from this numerical problem that here the major thing we determine, that is that whether the flow is laminar or turbulent, and then we apply those empirical correlations according to the situation to get the value of H, which was given to you in the conduction analysis by your uh, in the problem data. But now in the convection, the determination or the calculation of H is the major thing which we would be doing in all these chapters, in all the topics which we are going to discuss. The calculation of Nusselt number and then subsequently H value, that would be the major thing or the major task for the convection problem. So is there any query? If you have got any query, you can ask. Otherwise, I can take attendance, and then